So here we're going to finish off this chapter by, looking at our other couple of functional groups, the ethers and thiols. So we're going to look first at the ethers in terms of their physical properties. So what do we want to start with? Well, we're going to start with looking at its solubility. So in general, very little water solubility. In fact, little enough that for most practical purposes we can assume that ethers are not water soluble at all. What about their boiling points, melting points? So we're going to compare 4 different compounds here. We have our ether with 4 carbons. We're going to compare that to an alcohol with 4 carbons. That way those are 2 compounds that have the exact same molecular weight. We're going to compare it to sort of half an ether, an alcohol with 2 carbons. And then we're going to compare it to a 5-carbon hydrocarbon, because that's going to be approximately the same molecular weight also. So ethanol, we've seen before, boils at around 78 Celsius, and 1-butanol, due to the longer chain, a little bit higher at 117. Pentane, just being a hydrocarbon, we know is going to be low, 36 degrees Celsius. And then possibly surprisingly, diethyl ether, almost identical, 35 degrees Celsius. So it turns out that with ethers, having that oxygen in there doesn't really do much to strengthen the intermolecular forces. And so in terms of things like melting point and boiling point, ethers behave pretty much as if that oxygen's not even there. So what do we do with ethers? Well, it turns out ethers aren't all that reactive. There's some exceptions, which you can get them to react under strong acid and high temperature. Under those conditions, you can actually get your ether to basically fall apart into the 2 halves. But the other reaction, and sometimes this is one of the most important reactions of ethers, is if you leave a bottle of some sort of ether around for years. Sometimes you might come back to it at that point and find that there's this white powder on it. And it's over time, as your ether is exposed to oxygen and to light. So this is actually one of the reasons that when you buy ethers, a lot of times you find them in opaque cans. They come a lot of times in silver cans that light's not going to get through to. And we have to do that because if you get too much oxygen and over too long of a period you expose your ethers to light, and this isn't something you have to worry about in a few minutes in the lab. It takes months, if not years. But that ether can add a second oxygen in there, making a peroxide. And what's the issue with peroxides? Well, many, especially low molecular weight epoxides, like the types we'd form from common ethers, are quite explosive. And so a lot of times, we have a limited amount of time before we, need to dispose of an ether after we've opened it. But for the most part, ethers don't really do anything else that's all that interesting. In fact, the most common purpose of ethers is that we use them in the lab as solvents. So our other functional group to look at here are thiols. So thiols, as we talked about previously, are most commonly noted for their smell, giving the scent for things like rotten eggs or skunks spray. How do their properties compare? Well, that SH bond is not really polarized. Same thing with the carbon-sulfur bond. Now there is a little bit of polarization, so it's better than just having a hydrocarbon. So we can compare this 1-carbon thiol to both a 1-carbon hydrocarbon as well as a 2-carbon hydrocarbon that's more similar in molecular weight. And we can also compare it to an alcohol. And so we can see here that we do actually get pretty good increase in boiling point compared to a hydrocarbon, but not nearly as significant as an alcohol. So what these numbers tell us is that in a thiol, there is some polarization, there is some increased attraction compared to a hydrocarbon, but it's not all that strong. It's nowhere near the level of an alcohol or, say, a ketone. So what can we do with thiols? Well, thiols, again, are another functional group that don't have that many uses or purposes. But they have one in particular that's really important. And that's another oxidation. So if you take a thiol and you oxidize it, well, that's too many carbons. You get what's known as a dithiol. I'm sorry, not a dithiol, a disulfide. And where do disulfides matter? Well, there's one very, very specific type of disulfide that is actually fairly important. So if we look at our 20 naturally occurring amino acids, only one of them has a thiol in it. And we find it down near the bottom as cysteine. So what's so important about cysteine? And we'll just draw its structure again over here. Well, what do we know about the shapes of proteins? So when we deal with proteins, there's a number of different levels of structure. We can see some examples of that here. So when we look at the structure of the protein, we have 4 levels of structure. We have the primary structure, And the primary structure is literally the sequence, the order that the amino acids show up in. We then have the secondary structure, which is as those peptides start to bend and cause some specific shapes within the protein. You can see the two most common ones here, the beta pleated sheet as well as the alpha helix. Then eventually the entire structure of the protein folds into a shape. That's our tertiary structure. And then as we start putting multiple proteins together, that's when we get to the quaternary structure. And what are the things that control the secondary, tertiary, and quaternary structure? Well, two amino acids that might not be anywhere near each other on the chain, if the chain folds around in the correct way, might be very close to each other in space. And so there's a number of things that can influence that. And so it's things like hydrogen bonding, salt bridges, and van der Waals forces. And which one occurs all depends on the structure of the amino acid. But all of these so far are what we call intermolecular forces. Do we ever see any actual covalent bonds between two amino acids that are not next to each other? And there's only one way that exists, and that's with cysteine. So if we take two cysteine molecules and put them together, we can oxidize them. And we form these disulfide bonds. And these exist in proteins all the time. Again, these are the only actual covalent bond that exists between amino acids that are not directly next to each other. And these disulfide bonds are especially important in one specific protein, that being keratin. Keratin makes up our hair. And it's actually the disulfide bonds that control how curly your hair is. How many of those disulfide bonds and where they are in the protein. And so if you ever want to change how curly your hair is, well, basically what you do is you take some sort of reducing agent, and you break all of those disulfide bonds and convert them back to the thiols. Then you set the shape of the hair how you want it, and you apply an oxidizing agent. And that makes those new disulfide bonds in the positions where you wanted them. Now over time, as your hair grows out, that's why you don't see those anymore. The curliness always reverts back to what it is naturally. But at least for a time, you can change it. Alright, so that's it for everything in this chapter. You've got a practice sheet of reactions for each of these functional groups. So you should go ahead and try those, and we'll talk about the answers in the next video.